Hello students, welcome to the course Circuit Theory and Networks. Myself Milan Sasmal, Assistant Professor of Electrical Engineering and Department from JIS College of Engineering. And today we will discuss the resonance circuit. Resonance circuit means the circuit which contains some resistance, some inductance, some capacitance, and we have to check that what happens at the time of resonance, and slowly we will come what is actually resonance and what the effects are there and what are the different things or what are the criteria that will comes later. So before going to the course, just the key features of this particular chapter, that will be the resonance, obviously both series and parallel resonance and their frequency response. It means what happens if we changes the frequency, or what will be the natures of the circuit if we consider the circuit in lower ranges of frequency, or similarly in higher ranges of frequency, their natures, it means they are lagging or they are leading. Similarly, what will be the quality factor and what will be the half power point. It means whenever what is the condition or when the circuit will draw the half amount of its power, and what will be the phasor diagram for that condition, and what are the practical application and what are the purposes of this, that we will see. And at the end of this session we will see the several problems, the numerical problems based on this theoretical knowledge or based on this resonance chapter. Okay, so let's start the session. Okay. So first of all, we are considering the series resonance. Series resonance means a circuit contains the resistance, inductance, capacitance, all are there and they are connected in series. And resonance means when the inductor and capacitors will have the same efforts to the circuits, and ultimately they neutralize the effect of each other, because as we know, the inductor tries to lags the current and similarly a capacitor tries to leads the current, and as they are having the opposite in nature, so obviously if a circuit presents both the inductor and both the capacitor, then what happened, they will try to nullify each others if they have the same effort to the circuits. So that types of condition is called the resonance condition. And when the resonance occurs, obviously as inductor nullifies the effect of capacitor, or vice versa, as the capacitor nullifies the effect of inductor, so obviously the circuit will have only the effect of resistors. And we know, if a circuit having only the effort by resistors, obviously the circuit will be purely resistive circuit, and we know for a purely resistive circuit, the power factor is always unity. And obviously there will be some changes of uh, impedance throughout the circuit based on their frequency, because in a particular frequency the circuit will have a particular impedance. Similarly, if we change the frequency, they will have the different impedance, so that we will check. Okay, so it's a simple series circuit. RLC is given over there, and R is resistance, L is inductance, and C is capacitance, and we know. And for the simplification of the circuit, we have to consider all the components, I mean resistance, inductance, capacitance, in terms of ohms. It means resistance, it's already in ohms, so we have to consider this inductance as a inductive reactance, and capacitor is also inductive reactance. And we know that for inductor, we know that is plus of jxl for inductor. If we inductor L, unit is Henry, and similarly for the inductive reactance, that is J of XL, that we know that inductive reactance, that is JXL. XL means inductive reactance, and we can write it XL as the omega L, so we can write J omega L. Again we know omega is equals to 2 pi f. Again if we put the values of omega, that will be J into 2 pi f into L. Similarly for capacitors, and this one will having the unit, that will be J omega L, having the unit of ohms. And similarly C, capacitor, having the unit of farad that we know. Similarly, for this capacitor, if we consider the capacitive reactance that we can write, that is minus of jxc, minus of jxc, minus of jxc. So similarly we can write minus of xc minus of j, xc means 1 by omega c, so we can write divided by omega into c. So obviously overall unit will be in ohms, so we can write in this way. And again here is written 1 by j omega c. It's nothing the same thing, just if we multiply the both the numerator and denominator by j, or simply if we multiply it by j over here and similarly 1j over here, it will comes to this equation. Okay, so how it will be? It will be j square. J square means minus 1. J square means minus 1. Minus 1 minus this minus, that will be plus. So plus 1 divided by j omega c, that we can write. So no problem. So for inductor, we can write the inductive reactance as a j omega L, or we can write for capacitor that is 1 by j omega c, or we can write minus of j by omega c. Any one we can choose. And the voltage that is given as a Vs is equals to Vm angle theta. This is the magnitude Vm, and these are the angle that is given over here. Okay, now for this series resonance condition, series resonance circuit, the simple RLC, they are connected in such a way, and voltage source is given over here. Now if we find out the impedance, if we want to find out the impedance is nothing but that we know Z is equals to V by I. If we consider simply we can get this one, or you can get this one by using your KVL also. By simple KVL you can write it as a, suppose I into R plus I into j omega L plus I into j omega L plus I into 1 by j omega c. It means we can write I into I by j omega c, and minus of Vs means Vm angle theta, or minus of Vs, if we can write, that is equals to, we can write over here that is 0, or simply if we take this Vs in the right hand side, it will be simply is equals to Vs. We can write is equals to Vs. No problem at all. Now if we take a common as a I, so this part contains R plus j omega L, R plus this part only j omega L, plus this part only 1 by j omega c, this part, and 1 by j omega c is equals to Vs. If we write over here is equals to Vs, then we can write Vs voltage divided by current, that is equals to R plus j omega L plus 1 by j omega c. That term is written over here. Okay, so we can write again, if we take a common of j, we can write R plus j into omega L minus of omega c. It's nothing but if we take a common of j, nothing but we are multiplying with j over here and j over here, that will be j square. So it will be minus of j by omega c, that we have seen in earlier. So the overall equation, it comes like this. This is the overall equation. Now as you have seen that the resonance condition is nothing but when the circuit have the inductor and capacitor same effort. It means inductor and capacitor, they will nullify each others. Okay, so if they nullify each others, so their effect will be neglected. Now just take an example of what happens actually. Suppose as we know that inductor tries to lags the current, and similarly capacitor tries to leads the current. And now what happened, if we take an example that suppose a door is there, and the door can be opened in both sides. The door, suppose the door is there, this door can be opened either in this side or in this sides, in both sides. This is wall. Okay, now suppose one person is pushing at the door, and the another person is also pushing the door in this side. Okay, so what happened, who will provide the more energy the door will possess in that side. Similarly, the inductor and capacitor, they also tries to send the current in two different direction or two opposite direction. Suppose inductor tries to lags the current and capacitor tries to leads the current, and if when the circuit presents both the inductor and capacitor, they try to send the current in lag and leads, then their ultimate effect on the circuit, that will be the resultant of this inductor and capacitor. Similarly, for this case also, if the two peoples are applied same amount of force to the door, then what happened? The door will be at this particular position. Door will be at this particular position. Similarly, if the inductor and capacitor will have the same effort, then what happened? The inductor and capacitor, they will nullify to each other, and the circuit will have only the resistive effort, right? So this condition is called the resonance condition. Now let's see how we can find out the resonance frequency. So one thing is clear, that the resonance will occur when the inductor and capacitor will have the same effort, and as per this series circuit, the inductor and capacitor effect means the overall part, this omega L minus 1 by omega C, obviously this J into this term. So this is the overall effort. So this effect will be cancel out. So if this effect will be cancel out, so obviously we can say that our omega L minus 1 by omega C is equals to 0. So we can write omega into L is equals to 1 by omega C, and if we multiply it, that will be obviously omega square into LC is equals to 1, or if we can write omega square is equals to 1 by LC. Obviously we can write omega is equals to root over of 1 by LC. We can write root over of 1 by LC. And so this is the frequency for which the resonance occurs. That's why this frequency is called the resonance frequency, or sometimes we denote as omega R, or sometimes denote as omega 0. So this frequency, that is called the resonant frequency. It means for which the resonance occurs, or at which frequency the resonance occurs for that particular circuit. That frequency is called the resonance frequency. So we can calculate the resonance frequency in such a way. Now again omega 0 means we know 2 pi f. So again we can write 2 pi f 0, that is equals to root over of 1 by LC. If we can write it, so we can simply find out the frequency directly. Rather than angular frequency, we can directly find out the direct frequency, that is f0, that is equals to 1 by 2 pi into root over of 1 by LC, or root over of 1 by LC. So that is written over here. So we can find out resonance frequency, as well as we can find out the frequency, the normal frequency for which the resonance occurs. So this formula is very important for our further calculation. So try to remember this thing, and this will be very important. Okay. Now for this circuit, suppose in practically we are making these types of circuit, and we are taking the voltage against this across this resistance. So if we consider the voltage across this resistance, that will be suppose VR, only the voltage across this. So suppose VR is the voltage across this resistor. Similarly, VL is the voltage across this inductor, and VC is the voltage across this capacitor. If we consider the voltage, and if we change the frequency of this supply, then we will see that the voltages are changing, and sometimes it may happen that voltage across this inductor or across the capacitor, it may increase the there may be the excess amount of voltage than the supply one. It may happen. So if we take this voltage across this resistor, across this inductor, and across this capacitor, and if we make a graph, and we will find one types of nature, and based on this frequency, we will getting these types of curve, for voltage across inductor, voltage across capacitor, and as well as voltage across inductor. So in the next we can go for that. Okay. So where is the graph, and if we plot the graph based on the frequency, the x-axis that denotes the frequency obviously, and this y-axis that denotes the voltage. Voltage means sometimes we have considered the voltage across the inductor and all is the voltage the capacitor, and if we plot it separately, then suppose we are getting these types of graph. Suppose if we consider the frequency versus voltage across the capacitor, frequency versus voltage across the capacitor, we are getting these graphs, this one. Okay, so whenever we are increasing the frequency, the voltage across the capacitor that is increases, and after a certain time or after a certain value, the voltage is again decreases. And similarly for the inductor also, the voltages, if we start increasing the voltage, increasing the frequency, the voltage across the inductor starts increasing, and after a certain time it goes to maximum, and then it goes to reduces, reduces. And so, and in the mid, and in the cross point of these two voltages, where actually we obtain the fs, means the resonance frequency, like that. And now if we consider the voltage across the resistance also, then also we are getting these types of graph, actually how it's coming, that I am coming to later. And similarly if we consider the current graph with respect to frequency, then also we are getting these types of graph. Okay, so normally how we can calculate this voltage, or if we want to calculate this voltage, simply we can go for the normal calculation, that is that we know in our equation, the overall impedance that was R, R plus jXL, R plus jXL minus of jXC, that is the our overall impedance of the circuit. And if we put the values of XL and XC, and our actual value was R plus j omega j into omega L minus j into omega L minus of 1 by omega C. Omega L minus of 1 by omega C. Now for this case, our current, this was the overall impedance, that is our Z, So for the resonance or any other condition, our current, will be I is equals to V by Z, obviously that we have already calculated, V by Z. If our supply voltage, that is the fixed one, voltage is fixed one, just we are only changing the frequency, then based on this Z, our I will be changing. And the voltage across the resistance VR, that if we can consider this VR, that will be obviously this I into R. And similarly voltage across the inductor, that will be obviously this I multiplied with this omega L quantity, and similarly voltage across the capacitor, that will be I multiplied with this quantity, right? Now whenever we are increasing the frequency, then what happens? Whenever we are increasing the frequency, if f is increasing, this here is omega into L, this omega into L, it means omega means 2 pi into f, so omega into L, this omega L, whenever we are increasing f, this f frequency, our omega L will be always increased, because XL is equals to 2 pi FL, that is written over here, 2 pi into FL. So if we increase our f, so our XL will be increased, so that we can write in this form. So it will provide us a straight line, because 2 pi and L, that is the constant, we are not changing this values of this L, so it will be a straight line. So if we increase the frequency, then our inductive reactance will also increase. Similarly for this capacitive reactance, that is J in minus of jXC, or that is minus of J by 1 by omega C, that is written, and XC is equals to 1 by 2 pi of FC. So if we increase this F, this F quantity, and keeping this C as a constant, so we will see that XC, if we increase this F, and XC will decrease. So similarly at the increment of F, our XC value is decreasing. So we are getting these types of graphs. So actually whenever we are plotting this XL and XC in the same graph, we are getting, this is the graph for XC that we have obtained over here, and similarly this is the graph for XL that we have obtained. And if we put it over here, there is a cross point. So this cross point means, and in this particular point where the inductive reactance and the capacitive reactance are the same, and when the inductive reactance and capacitive reactance are the same, then what happened? Then the resonance occurs, that we have already seen. So this point where the resonance will be there. Now when the resonance will be occur, what will be that frequency? That frequency will be called the resonance frequency. So this is the resonance frequency. Now before this resonance frequency, if we look carefully in this graph, it is clearly visible that before this resonance frequency, the circuit having the inductive effect only this much, maximum of this much is the inductive reactance effect, but the capacitive reactance effect is the more. So before this resonance frequency, the circuit having the capacitive effect, so that's why it's written that XC is greater than XL, and after the resonance frequency our XL is greater than XC. It's very clear from this graph that after this resonance frequency, suppose if we consider that this particular frequency, when the inductive reactance is this much, and capacitive reactance is only this much. So it's clear that for this particular frequency, let's say this frequency is Fx, so this Fx frequency where the inductive reactance is very much greater than the capacitive reactance. So obviously at this particular frequency the circuit will have the inductive effect, obviously the circuit will be lagging. And similarly, this is nothing but this is the impedance, this is the overall impedance. As we know that based on the frequency, whenever we are changing it, our XL and XC they are changing, but our resistance is fixed, there is no more changes for the resistance. So based on this, and in this particular point, in this particular resonance point, when XL is equals to XC, that already we have seen, then our impedance Z, that will be only R. It means this inductor and capacitance effects will nullify to each other, so this overall part, this will be 0, this part will be 0, so our Z will be only R. So as the previously our impedance was R plus of something, now we are getting Z is equals to R is equals to only 0. So we can conclude one thing, that in case of series resonance, at resonance frequency the impedance is minimum, and other than this resonance the impedance is more of that resonance frequency, right? And if we draw the graph, we are getting these types of characteristics, and this is the minimum point, that is the values of the resistance, and this minimum point can never be 0 because the circuit contains some amount of resistance, and this is the values of resistance for the when the resonance occurs, right? And before the resonance there is also circuit having the more impedance than the resonance condition. Similarly after resonance there is also the impedance which is more. And now one thing is clear, if at the resonance condition the impedance value is minimum, the Z is minimum at resonance condition, if the impedance is minimum, this Z is minimum, then what will be I at resonance condition? That will be obviously maximum, because I is equals to V by Z. If my V is constant, and if we change this Z, based on this Z our I will be changes. So when the Z is maximum, at this particular point, if the Z is there, obviously our current will be like that. Similarly, then it will be when the impedance decreases, our current will be increases, and when the impedance is minimum, then our current will be maximum, and after that when again the impedance increases, again the current will decrease. So we are getting these types of characteristics for the current. We are getting these types of characteristics. Okay. Now as you have seen that before the resonance frequency the circuit will have the capacitive effect, and after the resonance frequency the circuit will have the inductive effect, as per the previous circuit that we have already seen, this one. So if we want to make the phasor diagram for this, then obviously here the capacitive effect is more. It means obviously if we can consider the current, capacitor always try to leads the current. Okay, so it means if this is our current and this is the phasor for the voltage, one thing. This is for the voltage. So if you consider the voltage has been started from over here at the 0 point, similarly our current, as the current leads, it means for the capacitive effect, so current have to start earlier of some angle theta. If we consider that the current leads by an angle theta for this capacitive effect before the resonance frequency, and similarly at the resonance point, capacitor and inductor will have no effect. So here the circuit will have only the resistive effect, and when the circuit will have only the resistance effect, and we know the power factor that is that we can consider of cos phi, that we know the power factor that is cos phi. Cos phi is equals to that we know R divided by Z, R divided by Z, and at resonance, and in resonance series resonance condition, Z is equals to R, and at resonance Z is equals to R. So at resonance we can say that cos phi at resonance R, if we can write phi R, cos phi at resonance, so that will be R by R, Z is equals to R, so that will be 1, right? So unity. So at resonance they will be unity. It means voltage and current, they will be in same phase. It means there will be no more phase difference. So if we start from here, so this is if this is our the graph for voltage, and this will be from the same point our current will also starting, and it means voltage and current, they are in same phase. And similarly after the resonance frequency, as the inductor will have the more effect in the circuit, so we can say XL is greater than XC. So it means as the inductor tries to lags the current, so it means voltage, this is our voltage. It means after starting the voltage inductors, the current starts after few time or after few degree. If the current lags by an angle theta, it means after angle theta the current phasor will be over here. So if we draw it in such a way, so we will see for this capacitive effect, we can say if this is our voltage, if we consider this, if this is our voltage, current leads by an angle theta. So current leads by an angle theta. So this will be I, and current leads by an angle theta. And for this case at resonance, if at resonance what happened, if this is our V, and there is no more angle difference, if this angle between voltage and current, that will be 0, 1. 1 means cos 0, 1 means cos of 0. It means angle between voltage and current, that is 0 degree. So 0 degree angle means if this is our V, means voltage, so current will be also over here, V and I will be over there. Similarly for in case of inductor, we know the inductor try to lags the current. So if this is our voltage, voltage is over here, and current starts its journey after an angle theta, it means we can say the current lags by an angle theta. So if this is our V, it will be our I, lags by an angle theta. This angle is theta. So look it carefully, here current leads and here current lags. So look this thing carefully, and this is for the effect of resistance, inductance and capacitance for the circuit and the resonance. So till up to this point we have seen what is the resonance, what is this RLC series circuit, and how the resonance occurs, what will be the resonance frequency, how we can calculate that resonance frequency, and how will be the effect of resistor, inductor, capacitor based on the changing frequency in the circuit, and what will be their responses. And we have checked what will be the power factor and what will be the overall effect of the overall nature of the circuit. Okay, that's all. Thank you.